Hi everyone, this is my presentation on using machine learning to predict energy production. For some personal background, my name is Jhanavi Hegde. I'm a junior at Mountain View High School in the Bay Area, California. I'm really passionate about environmental sustainability, and I'm involved in political advocacy and volunteering in the area. I'm also really motivated to do research where data science and environmental sustainability overlap, and that's generally an area I'd like to pursue in the future. My mentor is Dr. Archie Tram. He has his PhD in biomedical engineering from The Ohio State University. He's currently a senior data manager at Johnson & Johnson MedTech, where he works at the intersection of healthcare and data science. So looking into the larger picture of our project, the topic of reducing energy imbalance costs is a challenge that's been propelling environmental discussions for some time now. In recent years, climate scientists have been asking, how can we reduce energy usage and ultimately fossil fuel consumption? Now, energy imbalance presents a serious issue for several reasons. First, imbalance costs can manifest into higher expenses for energy producers, like the power sector, energy consumers, like us citizens, and the government. Imbalance costs also further prevent the allocation of money and resources towards sustainable efforts in optimizing energy. Additionally, the overproduction of energy contributes to the unnecessary production of fossil fuels, which also contributes to the greenhouse gas emissions and air pollution. Furthermore, risks associated with power grids, like blackouts or brownouts, are higher with increased amounts of energy being generated. So for some background on our project, we decided to look into the Enefit Challenge. And so Enefit is a large energy company in the Baltic region interested in implementing sustainable energy practices through predictive modeling. They proposed the Enefit Cackle Challenge, which was open to data scientists all around the world. And the challenge ultimately aimed to tackle the objective through an energy prediction model to balance energy consumption and production. So the challenge gave publicly available data for participants that included weather details, climate information, energy costs, energy sources, and some key aspects of the challenge. Publicly available data for all participants, like I mentioned earlier. And as for the score was measured in the mean absolute error of the prediction of energy consumption or production. And essentially, the smaller the error between the prediction results and the actual results, the more accurate the prediction model. And so what we began our project with. To begin, we started by compiling the various data sets available to us into one. So we combined client data, historical weather data, forecast weather data, electricity prices data, gas prices data, location data. We combined all of that into a singular data frame. We then processed the data through feature engineering. Now, feature engineering is essentially the process of transforming raw data into a usable format by creating distinct features for a prediction model to work with. For example, we created a time period feature that accounted for the hour, week, month, and so on. And so once we had these materials ready, we were prepared to begin. So for our initial approach, we applied the XGBoost decision tree to predict energy production and consumption. XGBoost, or extreme gradient boosting, is a machine learning technique that improves prediction accuracy through the creation of a decision tree. And so as you can see on the screen here, a decision tree is a flowchart-like structure that reaches an outcome through the passing through a series of decisions. And the more decisions you have, the more accurate your predicted outcome will be. XGBoost works by creating multiple decision trees and utilizing multiple functions, such as gradient boosting and weight placement, to produce a prediction. Regularization in XGBoost is used to prevent overfitting. Overfitting is when a model makes accurate predictions, but solely on limited data that it's trained on. And this eventually makes a model unable to take in new data and continue to make accurate predictions. And so this graph here represents the weight or significance of each feature or category of data that represents a factor in the prediction making. Each category represents a node of the decision tree. And so the highest feature, target 2 days ago, represents the same target variable that we're essentially trying to predict, but from 2 days earlier. And so based on this graph, we can assume that target 2 days ago is one of the first noted of the decision tree, as it has the most influence in the decision making of the prediction model. As the target 2 days ago data was the most recent data available to the model, we hypothesized that a target 1 days ago feature would be of even greater importance. And so here, having learned of the importance of recent historical data to the model and that there was a 2-day delay in the data, we attempted to extrapolate the target 1 day ago. Each target here represents a different row of the data set, as we chose to plot just a small range of the larger data set, which contained over 2 million values. And the target refers to the predicted consumption of that day. Now, we attempted to extrapolate the historical energy production data from the previous day using older data points. However, we didn't find a clear trend, as evident in the graph here. And so we had to change our approach according to our observations from the first approach. We knew that the implementation of XGBoost was successful in contributing to our model. However, the implementation of the target 1 day ago wasn't exactly the best method. And so we turned to a more holistic approach by taking the mean of the data points. And we observed that the approach of a mean target days ago instead was used by many other notebooks with the best scores. And so with the implementation of the mean target days ago, the model shifted its weight towards that feature. Previously, the most important feature had a weight of 81.4%. The new most important feature had a weight of 82.2%. From our work, we were able to conclude that the XGBoost regression model and implementation of the mean target days ago were effective in improving our model's accuracy. Some other important aspects that also played an important role in the creation of our model included the compilation of various data sets into one and feature engineering. Our energy prediction and consumption predictive model has the potential to minimize energy waste and human reliance on non-renewable energy sources. I believe that predictive modeling will have a large role in solution finding in the context of sustainability. Currently, predictive AI is being used in the context of sustainability in various ways: carbon offsetting, efficient building electrification, precision agriculture, and more, all of which are super interesting and I hope to look into in the future. All right, thank you.